If you can't hold it, you don't own it. This phrase usually implies a lack of control or strength. But in robotics, this logic breaks down completely. A robot arm can lift 500 pounds with ease. It has 50 times the grip force of a human hand. Yet, when asked to pick up an egg, that same machine often crushes its target into dust before it even lifts off the table. The failure is not about power. The problem lies in the millisecond-scale feedback loop required to adapt grip force without crushing or dropping fragile objects. Today, we are unpacking the mechanical story behind why holding on remains one of the hardest challenges for intelligent machines and what that means for the future of physical ownership. We often assume a robot drops an object because its artificial intelligence is too simple or its vision system failed to recognize the item. We blame software hallucinations or bad code. But the reality is far more fundamental. It is a question of mechanical compliance versus rigid control theory. Current computational models, which we rely on to simulate how robots interact with the world, often treat sensors as simplified binary points. Research from 2006, published in the Journal of Integrative Neuroscience, demonstrated that these point-like representations fail to reproduce the complex cytoarchitectural differences found in biological tissue. In simpler terms, software simulations alone cannot replicate the nuanced tactile feedback required for dexterity without physical hardware integration that mimics human skin and muscle structure. This leads us directly into a critical design flaw we see across almost every robotic hand on the market today. A study by Almeida et al., presented at ICNSC in 2025, reveals that most robotic hands concentrate sensors only on their fingertips. This creates a massive blind spot during manipulation tasks. Optimal in-hand movement requires distributed touch across palms and finger pads to detect slippage or pressure distribution changes that optical vision simply cannot see. Relying solely on fingertip data means the robot is effectively blind to how an object shifts inside its grasp until it has already started falling. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Furthermore, we must address the limitations of relying purely on visual systems for physical interaction. Purely visual approaches fail catastrophically with occluded objects, transparent surfaces like glass, or items with low contrast where optical sensors lose their depth cues entirely. Tactile feedback is the only modality that remains robust in these scenarios, acting as a ground truth for control policies when vision fails. Without this sense of touch, a robot cannot distinguish between holding a smooth stone and a fragile egg based on visual data alone. The system lacks the immediate physical confirmation needed to adjust its grip force before damage occurs. This brings us to another major bottleneck: the translation of human motion into machine commands. Recent position papers argue that scaling vision language action models hits a hard wall because physical interaction data lacks inherent labels. Unlike text or images, force signals and torque requirements are not naturally digitized in human demonstrations. They require specific embodiment interfaces to translate raw physics into actionable robot commands. We cannot simply download human dexterity into machines. We have to build sensors that detect micro-deformations in milliseconds. The challenge is one of mechanical design and control theory, not just neural network architecture. Because of these constraints, the drive for five-fingered hands is often a design bias rather than an engineering necessity. We tend to anthropomorphize our machines because we want them to look like us, but nature has already solved this problem through specialization. Data from the DARPA Robotics Challenge shows that 15 out of 25 successful teams utilized under-actuated 3- or 4-finger grippers. Amazon's picking champions have similarly found great success using suction cups and specialized end effectors rather than complex human-like hands. True dexterity relies more on wrist flexibility and finger abduction mechanics than on matching human anatomy exactly. The core thesis here is that true ownership of physical objects requires mechanical compliance, not just digital cognition. A robot that cannot adapt grip force within milliseconds is functionally blind to the object's fragility, regardless of how advanced its neural network claims to be. When we see a robot drop an item in a demo video, it is rarely a software glitch or an AI hallucination. It is a fundamental physics constraint where the control loop between sensing touch and adjusting motor torque is too slow for fragile interactions. We are trying to solve a biological problem with digital speed limits that do not exist yet. The path forward involves moving away from generic attempts at human mimicry toward specialized tactile skins or underactuated grippers designed specifically to feel their environment rather than just see it. The engineering reality dictates that we cannot simply code an egg-crushing force limit. The system must physically sense and react faster than the time it takes for a muscle fiber to fire in response to pressure changes. Until we bridge this gap between high-speed actuation and low-latency sensing, robots will remain clumsy with fragile items despite their immense strength. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.